Sketching surfaces in 3 dimensions is going to be pretty important throughout this entire course. So we're going to take a look at how to sketch one of the easier surfaces that we're going to talk about this semester, and that's how to sketch a plane in 3 dimensions. Now remember, the equation of a plane, as we saw last time, generally has the form of something like this, like 2x 3y plus 4z is equal to 12, something along these lines. How would we sketch this in 3-dimensional space? Well, it would end up being a plane somewhere out there in space, and drawing a flat surface that's infinitely large in every direction is pretty much impossible. Impossible. So what do we normally do is we just draw it as it crosses through different octants in our 3-dimensional space. Now we haven't talked about how we draw 3-dimensional space, or sketch it when we're on our own. Generally, the standard way that we do it is we draw the XY plane as flat, kind of coming out of the board at us, and Z now takes the kind of the Y direction, kind of going up and down. So this is generally how we draw our 3-dimensional grid. Now, with a 2-dimensional space that we normally have like an X and a Y, that breaks a 2-dimensional space up into 4 pieces or quadrants. Notice that this is now broken up into 8 pieces or octants. That's a little hard to point out, but the one right here in front, where everything is positive, is the first octant. Then of course I go 2nd, 3rd, 4th, 5th, 6th, 7th, and 8th, just kind of walks around. So take a look at a picture if you're not really sure, but to be honest, the one we're almost always worried about is the first octant, and that's where everything here is positive. So what we generally do, and we're going to see a couple ways to do this, the way that we sketch a surface going through the octants, we take a look at what does it look like as it crosses axes, where's it at when it crosses each axis, and what does it look like when it crosses each plane. These are called traces. What the graph looks like as it crosses an axis, or quadrant plane. Now what I mean by a quadrant plane, like the XY plane would be a quadrant plane. The YZ, that's the one that's flat in the board, is a quadrant plane. The XZ one, that's the one that's kind of coming out at us, that's a quadrant plane. So what does it look like? Well, let's take a look at as it crosses axes first. So as it crosses the x-axis, we're going to do all 4 here. Let's say as it crosses the x-axis. Well, what do I know about every point on the x-axis? Well, for every point on the x-axis, both the y value and the z value are 0. Both y and z are equal to 0. So if that's true, what does this equation become? Well, if the y and z are 0, that gives me 2x is equal to 12. That means x is 6. So if you take a look at the x-axis here, the graph crosses it at that single point. Again, let's take a look at the y-axis. For every point on the y-axis, that's the horizontal one, we can see that the x is 0 and the z is 0. So that would be x and z are 0. So if x and z are 0, what do we get here? Well, x is 0, z is 0, so we get 3y is 12. So y would be 4. So this thing's going to cross the y-axis right about there. Now, with the same logic, and let's go through this one a little bit quicker, for the z-axis, we know for every point on the z-axis, the other 2 letters are 0, x and y are 0. So if we put x and y equals 0, we get 4z is equal to 12. So z is equal to 3. All right, but how do we connect these dots? How do we figure out what it looks like as we go through here? So now, what happens as we cross the XY plane. Now this a lot of times when we cross the XY plane is called the XY trace. But think about it now. Now we're looking at the entire XY plane. What can we say about every point in the XY plane? Every point in the XY plane, the Z value is equal to 0. So we get Z is equal to 0. Well, if Z is equal to 0, what we end up with is 2x plus 3y is equal to 12. Okay, that's the equation of a line. So we know in the XY plane, as we cross the XY plane, we end up with a line. And not only do we end up with just a random line, we know what the equation of that line is. That's 2x plus 3y is equal to 12. As we cross, let's say, the YZ plane. That's the plane that's actually flat in the board for us right now. So here you can see flat in the board, the x would be 0 on that plane. So our equation, if x is 0, is 3y plus 4z is equal to 12. That's also a line. So there's a line connecting these 2 points. And again, not only do we know it's a line, we know the equation of that line is 3y plus 4z is equal to 12. In the last case, we got what the xy, the yz. What about the xz plane? We know in the xz plane, the y is equal to 0. So we get 2x plus 4z is equal to 12. You could reduce that if you want, of course. Now in this case, again, that's a line, so then we know that there's a line connecting those two. And the equation of that line is 2x plus 4z is 12, or x plus 2z is 6. Okay, so there you go. To draw a plane as it crosses the first axis, the easiest way to see it is this. Find out where it crosses the x, y, and z axis, those points. Now in this case, since this is a plane, we know it's linear, which means everywhere it intersects something, it's going to be linear in this case. So really, we didn't really need these 3 pieces over here for this particular one, at least in the future. However, we are going to need these equations in the future, so we do need to know how to get them. So sketching a plane is very, very simple when you're talking about what does it look like when it crosses into the first octant. All right, something else that we're also interested in a lot is how do we find the distances between 2 things when we're in space or in 3 dimensions? And the kind of things we may be interested in is how would we find the distance between, say, a point and a plane? All right, let's start with a picture here real quick. So let's say that that's our plane, and we have some point out here for fun, let's just call it P. Now, first off, what in the world do we actually mean by the distance between a point and a plane? Well, if you were to draw a line from the point down to the plane, and it's perpendicular, that's what we mean by the distance. So this is actually what I'm looking for there is D. So how do we find that distance? Well, the idea here is this. I already know what direction that has to be. That has to be in the normal direction. If we know the equation for a plane, then we actually, just by looking at it, know a normal vector. So I'm going to put the normal vector here. Now remember, we can draw that vector anywhere that we want. I could have drawn it way over here. Just visually, it's a little bit easier to see. And I can always find a point in the plane. Out here, let's call that Q. Now, how in the world would we find a point if I just gave you the equation? So I have 2x, 3y, 4z is equal to 12. And I said, what's a point in that plane? Well, think about how we did it in 2 dimensions. If I gave you the equation 2x plus 3y is equal to 4, I said find a point on that line, what would you do? You'd pick a value for either x or y, you'd plug it in and you'd solve, right? If y was 0, x would be 2, right? So the point 2, 0 is on that line. I picked a value for y. Well, now that we have 3 variables, you're going to have to pick a value for 2 of them. So if you want to find a point on this plane, you let x and y be 0, that means that goes away. That means z has to be equal to 3. So there you go. You found the point on the plane. So it's always easy to find a point on the plane. So how do we actually find that distance? Well, here's what we're going to do. Since we're given a point, we have to be given that, and we're given the equation of a plane, which means we can find another point and a normal, we're going to find this vector here. The vector between a point in the plane and a given point. Now I'm going to want to find this distance here, so I'm going to take the vector PQ, or QP, doesn't matter. I'm going to project it onto there. So, where's blue? So I'm going to draw it over here just a little bit. So the blue there, imagine it being right on top. I'm just trying not to make it confusing. This will be the projection of, the projection of PQ onto N. So that would be that blue vector. Notice that would be if we took this and projected it onto the normal. Well, I don't want the vector, the blue vector, I want to know how long that is, right? I want to know the distance. So the distance between a point in the plane is the magnitude of the projection of PQ onto N, where N, of course, is the normal vector, and PQ is the vector between the given point and any point in the plane. Okay, so there you go. That will tell us the distance between a point and a plane. You just need a normal vector, which we're going to get from the equation of the plane, and the vector PQ, which is the vector between the given point, and a point in the plane that we'll be able to find. So let's go ahead and give this a shot. So find the distance between the point 1, 2, and 3, and I don't know, 2x, 3y, 4z is equal to 12. Nice easy numbers. All right, so the idea how to do this, we're going to need a normal vector. Again, we can find the normal vector just by looking at this equation. It's the coefficients of the x, y, and z. So our normal vector is 2, 3, 4. We're given our point P is the point 1, 2, 3. We need some vector in the plane. Now again, you can pick any vector that you want. We just did this a second ago. I found the point, 0, 0, 3. But any point in the plane will work. So let's just find the vector PQ, or QP. Doesn't matter what order you do this. So I'm going to do this minus that. So that gives me 1 minus 0 is 1. 2 minus 0 is 2. 3 minus 3 is 0. Okay, so now we have all the information that we need. Now we just need to find the projection of PQ onto N, which by definition is going to be N dot PQ all over the magnitude of N squared times N. Okay, so we need the dot product. So N dot PQ. So I'm doing this dotted with this. That's 2 times 1 plus 3 times 2 plus 4 times 0. All right, so that's 2, 6, and 0. So N dot P is 8. I also need the magnitude of N. So the magnitude of N squared, that's what we need right there, is just going to be 2 squared plus 3 squared plus 4 squared. Remember, we're not taking the square root because this is squared. So that's 4 plus 9 plus 16. What's that? 29. So putting this in here, we get the projection of PQ onto N is going to be the dot product over the magnitude squared times our normal vector. Now our normal vector here is 2, 3, 4. Now that gave us our projection. So that gave us the blue vector over here. So to actually find the value, we're going to do the magnitude of this. So the magnitude of the projection of PQ onto N is going to be the magnitude of 8/29, 2, 3, 4. Now I'm going to use a property that we saw, probably one of the first lectures that we said. It says if we're doing the magnitude of a constant times a vector, that's really just the absolute value of that times the magnitude of that vector. So this 8/29 is really just kind of in the way. So we can just pull that out as that and do the magnitude of 2, 3, 4, which is 8/29 times the square root of 29, right? That would be the same thing here, except for we'd actually take the square root of it. Okay, so there's our answer. There's the distance between those two. So it's 8 square roots of 29 over 29. Now you can actually clean this formula up just a little bit, and I'll show you that real quick, but there's the concept. You do the projection of the vector between the points given, one in the plane, onto the normal vector, then find the magnitude of that. Now, if you do this, I'll do this for you here real quick. I always just walk through all the steps, but watch this. If you do this, what we're actually looking for is the magnitude of the projection of PQ onto N. Well, we're told by definition that's N dot PQ over the magnitude of N squared. That's some number times the vector. Now, just like I used this over here, we're able to pull constants out front inside an absolute value. I can pull all of this mess inside an absolute value. So it's N dot PQ all over the magnitude of N squared times the magnitude of N, right? You still got to take the magnitude of that vector. Now, the nice thing about this, notice that these reduce, and I get N dot PQ all over the magnitude of N. Now, since the magnitude is the square root, I know that that's a positive value. So really all you got to do is do the absolute value of the dot product over the magnitude of N. So this will also give you the distance between the two of them. But this seems more like a formula to memorize to me than it does just find the projection and then find its magnitude. But you're welcome to use that formula if you'd like. Now also, what they may ask you is, how do you find the distance between two planes? Well, the good news, bad news here, that's a horrible plane, is the distance between two planes. Well, it only makes sense is if those two planes are parallel, right? Because if they're not parallel, then they're going to cross and the distance between them would be 0. So the way you actually do this is exactly the same way that you just did the point in the plane. Only difference is take one of the planes, find a point on it, just like we found a second ago, and treat it exactly like a point in another plane problem. So two planes works exactly the same way. All right, one last thing we'll look at here. How do we find the distance between a point and a line? This one's a little bit more difficult. All right. Okay, so now what we're looking at is we have some line in three-dimensional space and a point. Again, what we're talking about is the perpendicular distance, so we're looking for that distance there. So to be able to work this problem, we have to be given the equation of a line and we have to be given a point P. So that's what we're given so far. Well, if we're given the equation of a line, then we also know a direction vector and we can find a point on the line. So let's say we find the point Q. And just for visual sake, I'm going to put the direction vector U here. So, what we're going to do, kind of like before, we're going to find this vector PQ. Now we don't have a normal vector to a line here, so we can't do the projection type of thing. But we could find that distance, maybe if we did something like this. What if we put an angle in here? right? Because I know the vector u, because I know the equation of the line. I can find the vector PQ because I can find a point on the line and that's given. So I could use this angle to help me to find D there. Because you can see by trig, I can find the angle between two vectors. I'm looking for this and this. That would be the sine, right? It's the opposite and the hypotenuse. So from this, you can see that the sine of the angle is D over, well, that has to be a length of a side, so the magnitude of PQ. Or that distance is the magnitude of PQ times the sine of the angle. So technically we're done here. There's our answer. But I don't like this angle of theta in here, because that's bringing trig into a problem to where we actually can get away without trig in it. I'm going to use an identity we saw the other day. When we have two vectors here, like this, some u and v, has an angle theta, we saw that the area of this parallelogram was the magnitude of the cross product of those two vectors. We also saw, we did this in class, this was also the magnitude of u, magnitude of v, times the sine of the angle. Now notice, this is almost exactly what we have here, right? We have this angle, but we don't have the magnitude of this. So I'm going to take this up here, watch. That's the magnitude of PQ times the sine of the angle. I'm just going to multiply and divide by the magnitude of this vector, right? That's this vector down here from kind of from the picture. So I could say that this is the magnitude of PQ, magnitude of u, sine of theta, all over the magnitude of u. Well, the reason I want to do that is now I can turn this problem that has trig into it into something that doesn't have any trig at all. So the distance here would just be the magnitude of PQ cross u all over the magnitude of u, where u is the direction vector of the line, and PQ is the vector between the given point and any point on the line. All right, good news is it is just a formula here, so let's try one of these real quick. So, find the distance between 1, 2, 3 and the equations 2t plus 1, 3t minus 4, t plus 2. Okay, so here we have a line in space. Here's our parametric form and a point. So to use this formula, what all do we need? Well, we need the direction vector u. So our direction vector is just the coefficients of the t. So that's 2, 3, 1. We need a point that was given. Well, we're given a point P, which was 1, 2, 3. We need any point on the line. So to find any point on the line, just pick a value for t and plug it in. I don't care what value of t you use. I'm going to use t equals 0. That'll be the easiest. 1, -4, and 2. So we need to find the vector PQ. Again, I'm going to do P minus Q. Doesn't matter which way you do that. So 1 minus 1 would be 0. 2 minus -4 is 6. 3 minus 2 would be 1. Okay, so now we have everything that we need for this, except for we got to figure out what the cross product is, and let's go ahead and do that. So it doesn't matter what order we do the cross product, because we're going to find the magnitude of this. So PQ cross U will be IJ. Okay? PQ is 0, 6, 1. U is 2, 3, 1. All right, so in the I direction, that's 6 minus 3, I. In the J direction, that's 0 minus 2, j, and then the k direction at 0, minus 12. Okay, so let's see, 6 minus 3 is 3, 2, and negative 12. All right, so we can put all of our pieces together now. We need the magnitude of this. It's going to be the square root of 3 squared, 2 squared, and negative 12 squared. 9 plus 4 plus 144 is 157. And the magnitude of u is going to be the square root of, where's u at? 2, 3, 1. 2, 3, 1. 4, 9, 14. Okay, so since I'm out of room, I'm just going to kind of stick it right here. I'm going to go back over here. So our answer to this particular problem, the distance between that point and the plane, is going to be the square root of 157 over the square root of 14, if I did my arithmetic right. All right, now of course the book's most likely going to simplify this, rationalize it. Of course for me, I don't care if you rationalize or not, you go left it just like that. So finding the distance between a point and a plane and a point and a line is really just using a formula. Find all the pieces, plug it in, and watch your arithmetic.